Okay, well, good morning again, everybody. It's good to see people back again, and it's my great pleasure this morning to have the honor of introducing our speaker today, Evelyn Nsair. So I know most of us know Evelyn, but let me go ahead and say a few words of introduction just for anyone joining the group. Evelyn got her PhD in 1996 from University of Minnesota. And after doing a postdoc at Georgia Tech, she's been at George Mason University, where she's now a professor. She's the author of about 40 mathematical papers and a PhD supervisor of 5 PhD students. In addition to that, she's the editor-in-chief of what's arguably one of the most, if not the most, important journals in dynamical systems theory, the SIAM Journal on Applied Dynamical Systems. So I'm really looking forward to Evelyn's talk today on the mathematics of 3D printing. So Evelyn, it's all yours.
Thank you so much for the introduction. And I am pleased to give this talk. I just want to say this is mathematics of floating 3D printed objects. And the one thing that it doesn't have any of is dynamics. This is going to be about things that are floating in a static way. So maybe my first time giving a talk where there's no dynamics, but anyway, I'm excited to talk about this research. This is work that is an undergraduate research project starting last year, and we are continuing again this year. And the research is through our Mason Experimental Geometry Lab and also the Math Maker Lab, which is a small 3D printing lab that I run. And so just briefly, MEGL, I think you may have heard a little bit about it before, is a variety of things, but is basically sponsoring undergraduate research projects. And the Math Maker Lab does some undergraduate research, but mostly 3D printing, and including a class on mathematics of 3D printing. And so what I want to talk about today, just a sec, is joint work with a variety of people. So the top row is undergraduates and the bottom row is graduates and faculty. So Brandon Barreto-Rosa, Josh Calvano, and Lujain Nsair were the 3 undergraduate students that we worked with in the spring. Well, for all of last year, I was involved only in the spring, and Dan Anderson, my colleague, was involved for the full year and continues to be involved in the project this year. Patrick Bishop, Will Howard was a graduate student who worked with us last year, but he's not there anymore. But Patrick Bishop was involved in the technical pieces last year, and now is involved also in the research part this year. And we have 3 new students who are working with us this year as well. And so what I want to speak about is 3D printed objects and how they float. And before I move on to the picture, let me just go back to this picture. Here is an example of a 3D printed object floating in water. This M here is a physical, I mean, it's all virtual in some sense, but this is a physical version of this M, and this is floating in water. And so we printed a bunch of things and floated them in water. And the goal of this project is to try to understand how 3D printed objects float in water. And this is motivated by questions like, how do icebergs float in the ocean? And what happens when the icebergs change? How is the configuration going to change? This is of importance for things like calving, where you have large pieces of an iceberg fall off, and then the question is, how is the iceberg going to move and change in order to reconfigure based on the new configuration. And you can also have melting, which results in changes in the way in which the iceberg floats. There's a variety of cases in which this it's not just icebergs, but a variety of cases in which you might want to understand the stable configurations in which something floats. So I want to go sort of to the basics and try to explain the mathematics and, well, physics, whatever, math and physics behind the floating of icebergs and the floating of objects in general. So the first thing I want to do is talk about an object. And so I've drawn this little schematic diagram of a physical object. And I've tried, so it's all purple, but you can see there are some darker purple and some lighter purple pieces. And that's to sort of denote that the idea that you might not have a uniform density object. You could have an object with varying density, and the density of the object is going to be represented in this by rho as a function of x, where x is a point on the object. So then the mass of the object is just the integral of rho over this volume. The center of gravity of the object is 1 over the mass of the object times the integral of the x times rho of x dv. So this, in other words, now instead of integrating just rho, we're integrating x times rho. So this is going to be a vector valued object. So G is vector valued, but it's going to denote, and it may be a little small, but the green, sorry, the orange dot on this picture is the center of gravity of this particular object. Now, okay, assuming uniform density, I didn't do anything so this is the center of gravity. If this were uniform density, I didn't take into account the spots. This just was to denote that you could see it, but you can sort of see that this would be the center of gravity of the object. And in particular, one of the things that's interesting about the center of gravity is the center of gravity doesn't even have to be interior to the object at all. If you had some kind of a U-shaped object, you would expect that you could have your center of gravity totally outside the object. Anyway, so the idea now is we're interested in floating. So we're interested in floating things in water. So we need to understand how the object works within the water. So what I've done here is I've just added water. But what I want to point out about this is that the shape here is not a stable floating configuration. And this is important because this was something that I didn't really think about much. But in all the cartoons, this is exactly how icebergs float, right? The icebergs just sort of like are these large vertical things that stick out of the water and float in this configuration. In fact, this particular way that this object is shown would not be a stable floating configuration. It would actually turn over and lie flat sideways. Okay, so that's sort of one observation. But in order to calculate exactly how it would do so, one of the things we need to do is to calculate what's called the center of buoyancy. And the center of buoyancy is what I'm doing here is I'm saying, okay, this dark purple region here is the region of the object that is submerged in the water. And so you could submerge this object totally in the water or partially in the water, only a little bit in the water, and you would have a center of buoyancy corresponding to that submerging. And so what I'm doing in order to get the center of buoyancy is I'm taking one of the submerged mass times the integral over the submerged range of x times the density of the fluid, not the object itself, over dv. So in other words, what I'm doing now is instead of finding the center of gravity depending on the material that the object is made, this is basically the center of gravity of the fluid that has been displaced by this object. So the center of gravity is going to be somewhere, the center of buoyancy is going to be somewhere else, necessarily lower, because the, well, I guess it depends, but like if you have a piece of the object sticking up above the region, then you expect the center of buoyancy to be below, because you're only integrating over a part of the object. Okay, so anyway, with this in mind, we have the center of buoyancy, the center of gravity, and the goal now is to understand the what would you expect if you just let the object naturally float. Where would you expect to have, how much of the object would you expect to have be below the water line? And the answer is that the upward buoyant force exerted on an object, this is the Archimedes principle, is, if it's wholly or partially submerged, is equal to the weight of the displaced fluid. So in other words, the fluid displaced is going to correspond to the weight of the object in the water. Okay, so this can be written as the mass of the object times g. That's the force of the object is going to be the mass of the fluid times g. And so therefore, since you can write the mass of the object as the density of the fluid times the volume of the submerged fluid times g, what this says is that the volume of the submerged piece over the volume of the object is equal to the ratio of the well, so this is only going to be true if you have an object that has uniform density. It's going to be the density of the object divided by the density of the fluid, and that's what we're going to call R in what follows. And I should mention that if you have a object that is non-uniform density, you can still come up with a sort of an effective uniform density for that object and still establish an R for an object, even though it isn't uniform density. So keeping this in mind, I just want to give a few examples. An iceberg in seawater, you've heard people state, I mean, it's sort of a common thing to hear people state that 90% of the iceberg is below the water line, and that corresponds to an R being around 90%. And that just is saying that the density of iceberg divided by the density of an iceberg made of seawater divided by the density of the seawater is equal to 90%. So this is not, I don't actually know what the number is for freshwater ice cubes and freshwater, but presumably it's different. But I do want to mention something about 3D printed objects, and this is for freshwater, not seawater, that so I'm going to talk about this a little more in a minute, but each object, so when you 3D print an object, so a lot of what we printed were these little boxes. Okay, so but you know, we also did make these more oddly shaped objects as well. But anyway, for any of these objects, like this box, one of the parameters that you get to set is you get to set what percentage of the object you want to have filled. And I think I have one. This is sort of to look in on this object. I hope you can see that in general, the percentage of infill of an object is not 100%. You expect to leave some part of the 3D print empty when you're printing, and usually you have some kind of a grid pattern. I think I thought I had one here, but oh, here we go. You can see that, I don't know how easy it is to see, but see, this is a grid pattern of the type. So the higher the percentage infill, the more of the object you're going to fill with this grid. So you get a tighter and tighter grid depending on what your infill level is. So with this in mind, we did some measurements that for a 10% infill of filament, you get an R of around 0.3. For 50%, you get an R around 0.6. And for 100%, you get an R of around 1.2. 1.2 means that the object sinks to the bottom of the tank. Okay, so we have a certain level of leeway in being able to study these objects, because we cannot get 0% in, I should say, if 0% infill does not correspond to an object that is going to be zero mass, because no matter what your infill, you're always going to have a little bit of edge piece that is there. So we can't get to the very, very lowest possibilities, but we can get all the way to anything that doesn't even float anymore. So we have a fair amount of leeway to be able to work with these things. And in fact, the way in which an object floats is actually dependent on the on this R value. So with this in mind, here are some mathematical simplifications. The first simplification is that we're going to reduce the problem to a two-dimensional mathematical problem. I don't mean that we're printing two-dimensional objects. I mean that we just have a fixed cross-section along the third dimension, and it's going to be length L, where L is large enough that the object is going to lie with L being across the water. Okay, so lying like this, because L is long enough, instead of lying like this. It turns out you have to have it at least about twice as long as it is wide in order to guarantee that it's not going to be an issue in terms of the flotation. It's going to lie sideways like this. And it's just a matter of how it lies in the cross section rather than how it lies in the lengthwise dimension. The second simplification is this is a coordinate issue. In most of what I'm going to say, instead of moving the object around and looking at the water line as staying fixed, we're going to move the water line around and look at the object as staying fixed. And so this is a picture of what I mean here. I mean, obviously you can't change gravity, but you can change your coordinate system. So that we're going to just say, okay, well, when we want to study something, we'll keep this object fixed. And we'll say, okay, what if the water was at angle theta to the original? Now, in some of the movies and the pictures, I will show the water line as staying fixed because that's really how you'd expect to see it. But in the analysis, this is what we've done. And so just to say that, you know, so far what I've said is only about the Archimedes principle only tells you how far down in the water an object is going to float. But that doesn't tell you the configuration in which it's going to be stable. That only tells you how far down in the water it floats. And so in order to come up with a way of understanding the stability, we have to write down the potential energy. And that is due to Gilbert in 91, How Things Float. It's a very nice article. I recommend it. So this is the idea. The work done against gravity to displace an object of a certain mass, and I'm just assuming the L in the third direction, but I haven't explicitly put it in here, but you could therefore basically simplify things because you don't need to worry about this length. Is just given by the minus mg times this n is the direction the direction facing out of the water. That's why there's a minus sign dotted with the direction of the center of gravity. And likewise, we can do the same thing to say what is the potential energy due to buoyancy? The potential energy due to buoyancy, this is going to just be the work required to displace the fluid particles up to the air-water interface. And this is just going to be the mass of the fluid that's displaced times g n dot B, where B is the center of buoyancy. So this is basically the amount of work that would be necessary in order to take all of the water below the waterline and place it up to the top. So in another way of saying that is basically moving the object in such a way that the center of buoyancy lies on the waterline. And the dot product is simply because we don't care about anything but how but how far up it takes. You don't have to worry about anything else, so that this dot product just says the component in that direction. And so now, using the Archimedean principle, we can just and seeing that the mass of the object is equal to the mass of the object times g is equal to the mass of the fluid times g, it means that we can combine these two into one single potential energy. And this is the potential energy U of theta. And theta is just the direction of the water line, which I'm assuming, remember that we're moving the water line angle rather than moving the object itself, is just going to be the mass of the object times g times the unit outward normal direction as a function of theta, dotted with g minus the buoyancy. So the center of gravity minus the center of buoyancy. And I should mention that since we're not moving the object, the center of gravity stays fixed. But since we are moving the water, the center of buoyancy is moving, is a function of theta. So that's why the g doesn't depend on theta, but the b does. So I wanted to do just a little bit of a review of some previous work. There are some people who have looked at ship stability before. And even in ship stability, I just wanted to point out that you can already see that. So I should mention, I didn't fully mention this, but once you know the potential energy function, you know that the stable configurations would have to be minima of this potential energy function. And I just want to make a little point here, which is that since the dot product is going to be the norm of the first times the norm of the second times the and I should say the norm of this the norm of this is 1 because we're just assuming it's a unit normal. So the norm of the first times the norm of the second times the cosine of the angle between them. If you take the derivative with respect to theta, that gives you a sine. And so the places in which the derivative is 0, which could correspond to it could correspond to inflection points, it could correspond to local max, or it could correspond to local min. But the point is that those zeros of the derivative would be the points at which the sine of theta is 0, and the sine of theta is 0 when the g minus b has is going to be in the same direction as the water line. So in other words, the stable floating configurations would have the property that if you compare the direction of the water, so like the flat of the water, to the vector between g and b, they must be perpendicular to each other. Another way to say that is the center of buoyancy is going to be directly below the center of gravity. Okay, so this is sometimes stated as this is sometimes stated without developing this potential energy function first, but you can derive it from the potential energy function. So anyway, that's the way that we can find the stable floating configurations, is by looking for minima of this potential energy function. But what I want to do is just make the observation that there can be multiple stable configurations. So hopefully if you've ever been in a kayak, hopefully you didn't find out the hard way that there are 2 stable configurations of a kayak, but it is true. And if you're locked into the kayak, it's probably good to know how to avoid continuing to be in this upside down stable configuration. But this is also just to sort of point out that we won't just have one stable configuration for any given object. Icebergs have also been previously studied, and long objects with uniform cross-section, and this is the case that we're most interested in, have been studied before. These include squares, rectangles, equilateral triangles, but all with uniform density. Okay, so maybe it isn't clear from the way this is written. Uniform cross-section and also uniform density. And so one thing I want to point out is that there's an interesting, Ulam had an interesting conjecture, or maybe posed a problem, not sure right way to say it, asking what are the examples of two-dimensional shapes. So remember, this is long objects, so things like this, long objects which have no preferred floating orientation. And so here you can see the log rolling competition, right? This is an example. The circular cross-section is sort of an obvious example of a stable configuration of stable, no preferred orientation, any orientation, as long as you just roll it in the around, you're not going to have any preferred orientation. But in fact, that's not the only case. And here is a picture of this sort of heart-shaped region that also has the property that there's no preferred floating orientation. There's a whole, this heart-shaped one is the most appealing one, but in fact, in Auerbach's 1938 paper, he had a variety of different different options of this sort, like just with more, like a heart with more lobes, that also had no preferred floating configuration. In the case when the ratio of the densities is 1/2, there's actually quite a lot of floating, no preferred floating configuration shapes. But in the case when the R is not equal to 1/2, it's harder to come up with examples. And so this is a sort of an open problem to give us sort of a criterion for which floating configurations, in the case of not 1/2, you can have anything floating. We've decided, since we wanted to do experiments, we decided not to work with Ulam's problem. The main reason being that having uniform having no preferred floating configuration is something that is very sensitive to slight variations. And so the result would be that you're guaranteed pretty much that even though in theory it should have no preferred floating configuration, it would actually have preferred floating configurations. And we decided to not work on that problem simply because it's a case that does not lend itself well to experimental work. So there's now the floating square, coming back to the floating square, is the case that we've concentrated on mostly in this case. And so the question is, what are all of the floating orientations that are stable as a density ratio, as the density ratio is varied from 0 to 1? And so what I want to do is show a little movie. So this is a movie of basically how the square floats as you change the density ratio. And I should point out that there's not just, you can sort of tell from the symmetry of the square that when you see the object that is floating here, this is like density ratio essentially 0, that there are going to be 4 different ways in which this square would still have this floating configuration, right? I mean, you change it to its side, to its side, to its side, to its side, and all of those would be floating configurations that work. So in this particular picture, there are 4 stable floating configurations. As I show the movie, you will see that there are different numbers of floating configurations depending on the density ratio. So as it's going down, it's still considering, and then it turns. Now it's on its corner, and then if it gets down far enough, it's now floating with side down. Okay, so that's the sort of the floating configurations of the square. And summarizing that here, is a case. So this is saying, you know, as a function of the density ratio, what are the stable floating configurations as a function of angle? So in other words, we're letting the square just sit here, and we're moving the angle of the water line and asking what the stable floating configuration is. And it starts out being with the side down. Then it has a brief sojourn where it's sideways. And then it has the corner down, a brief sojourn where it's sideways, and then it has the side down again. So now we wanted to take this into the experimental setting. And so what we did is designed in OpenSCAD, which is a program for designing 3D printed objects, a regular square. This is pretty simple to do. This is the kind of thing that you can do without too much work. You see these holes that are in here. The goal of the hole is that eventually we want to move beyond just the square that is uniform density to a square that is non-uniform density. And in order to do that, what we did is we stuck, I don't know if you can see this, but there's a hole in here. And then we took a piece of a nail where my colleague Dan Anderson had the facilities to be able to saw off the end of the nail and make it the perfect length to be able to fit inside the hole. And then we were able to put this into the hole. You can possibly see that there's a nail in this one. So what that means is that this now has a non-uniform density, and it's going to have different preferences based on the fact that it's non-uniform density. Different preferences. I guess I'm anthropomorphizing it, but the point is that it's different stable floating configurations. So here is a picture of our sort of setup. There were a whole lot of, I have many of them here. You can see a whole box full of different objects, all of which were a combination of different density ratios, different positions of the nail, in some cases even different material. And here is a picture of how we did our measurements. We borrowed a nice high quality scale from the physics department so that we could actually test density ratios. We then had to float these objects in the water, and then there's a MATLAB sort of add-in where you can take a photo of this object and measure various quantities using, like, basically sort of identify different regions, different line segments, and use that to figure out this angle theta that we're working with in the experimental setting. And I felt sort of like it was a little bit strange to have these clips holding everything together, but then I recently did a visit to NIST, and they had a very incredibly high level, very fancy experiment that was held together with the same kind of clips. So I guess we're just experimentalists if we hold these clips.
They said that it was like the most precise thing.
Yeah,
the most precise measurement tool in the world for measuring the thing that it measured.
Yeah, so right, it was absolutely cutting edge, the most precise measurement tool in the world for measuring what it was measuring, and it was held together with the same clips. So I won't claim this is the most precise measurements in the world, but the clips were not the problem. So anyway, we decided on a standard of 30 by 30 by 60 in millimeters object, and then infill with and without hole were the measurements that we had to control the effective density and influence the center of gravity. This is a picture of so one of the things is I thought that, like the density ratio, that we would at least know what the 100% density ratio was for the PLA that we were working with. This is the filament we're working with, but it turns out that in fact the this is the measurement of the density ratio for 100% PLA is not something that is even standard from brand to brand. And so we had to go through and do a whole bunch of measurements. What we ended up doing after a while is not printing the whole thing, but printing little boxes like this, which take a lot less time to print, and using that to get at least the 100% infill case to use to figure out the density ratios. So I'm sorry if I'm focusing on the experimental side of things, but this is my first experiment. So you have to understand that this is very exciting to be able to talk about these things. But anyway, what we did then was for the square with uniform density, these are so just to point out that in each of these cases, different R values. This is a picture of R versus theta over pi, and these are the stable floating configurations. So the picture you saw before was just one little piece of this, but this is just to point out there start out by 4 stable floating configurations. Then after a brief sojourn, 4 stable floating configurations. But in here, there are 8 stable floating configurations. And this is the dots on this are experimental measurements that verify this. And these pictures here, what they're showing is for each R value, we can actually plot the potential energy. And so you can see where the local minima are of this picture, and you can just count up how many there should be, right? Here's the 8 stable floating configuration case. Here is a picture of what these, a sample of these 8 look like. And here is the floating object that is floating with that same floating configuration. So we were able to consistently reproduce this diagram in the cases of the 3D printed objects we worked with. But then we tried something else, and this is the cat infill was what sort of broke the symmetry. In particular, if you print with a very, very low density, and especially if you print with something like the cat infill, which is definitely not particularly reproducibly symmetric, what you end up with is just changing the center of gravity based on the infill. And so we decided to, instead of thinking of this as a downside, we would go for it as a feature, and printed things with these nails that I described. So now in this case of the non-zero center of gravity, so no longer at the center of the object, we were interested in being able to actually come up with, and we mathematically had equations for the stable floating configurations. You can see that things have gotten a lot more interesting. And so this is like, the reason there are these gaps is this is a bifurcation diagram that presumably has some unstable connections with the pieces that are stable. And so, presumably there's some most unstable, so critical points of the potential energy that are unstable that would connect up here. But anyway, a much more interesting picture of the stable floating configurations. And one thing that was interesting is that here we had that our prediction by our theory matched up nicely with our experimental measurement. Here, we ended up with 4 stable floating configurations, even though the theory only predicts 2. And so the question is, why would this happen? Well, the point is that I'll show you in a minute, but right near the case where you have the stable floating configurations only being 2, you have the stable floating configurations being all 4. And therefore, what we were picking up on was either a slight sensitivity in our measurement, or alternatively that it was just sort of like residually showing the stable floating configurations. And just to sort of show you what happens, here's the case of the potential energy diagram when the hole was at the center. So here is a potential energy diagram when the whole has moved over. We're assuming that this is a box that goes from -1 to +1 in both directions. So this is saying that this whole has moved to 0.3, and on the same diagram is nearby potential energy. And you can see that what's happening here is that at the potential energy that's being measured, you maybe don't have a stable floating configuration, a minimum of the potential energy right here at this red line. But if you were to change the whole, you would change the location of the hole just a little bit, you would actually pick up a new local minimum. And so we think that maybe there's a little bit of sensitivity to the hole, that maybe we didn't have the correct estimate of where the center of gravity was precisely enough. But the bottom line is that this is going to, because this is a chain, this is a bifurcation point in the potential energy critical points, you would expect to see this kind of problem in this case. So now I did want to talk a little bit about some more general statements, because remember, I also talked about the Mason M, which is, so if you specify, so you have a long object and you specify a general polygonal cross section via ordered vertices, then you can actually compute the center of gravity by using Green's theorem. You can write down a version of Green's theorem to say that it's actually just a summation involving the vertices. And in fact, the center of buoyancy is the same thing. You have to figure out where the water line is, but once you do, you have also a polygon for the polygonal cross-section shape of the object, of the part of the object below the water line, and therefore the center of buoyancy is also just a matter of computing a summation that involves just the vertices. And so once the water line is identified, then we can compute the center of buoyancy in a rather simple way, and therefore come up with a potential energy estimate at each, or a potential energy computation at each angle for this polygonal cross-section shape. And I should mention something about this, which is that the way in which you specify a 3D printed object is with a polygonal description. And so, in fact, the way that you have to define a 3D printed object is the same as this computation for the potential energy that we have. And so we were able to come up with a code. We took a general polygonal object and were able to identify the potential energy of this polygonal object as a function of the angle. And then for this case, but in general, also able to predict the stable floating configurations for that object. And in this case, you can see that our measurements were just about the same as you would expect for from the potential energy for the stable floating configurations. This floats in 4 different configurations. And this is another calculation. So the actual Mason M, the official logo of the university, has 3 feathers on it. So this is something that would be hard to do because these are disconnected, but you can do it as a theoretical object in our computation. We have code for this. And if it has 3 feathers, this is a stable floating configuration. If it has lost 1 feather, it's going to float in a different configuration. And this is an example of what in the case of an iceberg is called calving, where losing some piece abruptly changes the stable floating configuration. And so you expect to see it move quite a bit as a result of losing its, in this case, feather, but in general, an iceberg, a chunk of the iceberg. Our current and future work, so we're trying to move on to other types of things we can do from this fall. And one of the 2 cases that we're interested in is incorporating multiple fluids. So I thought this was a really entertaining picture because it shows the type of thing I'm talking about. If you have different fluids, one of the fluids is going to be lighter than the other fluid, it'll float on top. Think of oil and water. And you can have a situation like these raspberries here, where they sink in oil but float in water. And so then the question is, what are the stable floating configurations of the object now in this two fluid case? And there's no reason why the stable floating configurations between the two fluids would be the same as the floating configurations if you were lacking the oil. So in other words, you'd expect that, let's say, this object, it may float like this in just the water with air interface, but it may float in a different configuration in the oil water interface. And so we're interested in studying that possibility. Another case to think about, and you can hopefully see that there's surface tension showing here. This is something that would not be true, not be relevant for ships or icebergs. They're too big, too heavy for surface tension to be an option. But here, we think that one of the possibilities of why we were measuring something slightly different might also be a surface tension question. And so there's a paper by Keller that talks about the analysis of surface tension, and that's something that we would like to do. And I just wanted to sort of point out that there are surface tension options, one of which is water bugs, and there's been some work on water bugs related to the question of surface tension. And just in case you haven't seen this, you can actually similarly float a paperclip on top of the water using just surface tension. And I guess I haven't seen this, but you can also float a coin on top of the water if you do it carefully. So surface tension comes up in objects that basically are held up on top of the water, do not actually go into the water at all. And so this is sort of an interesting side remark of incorporating surface tension is, could we print a 3D printed water bug? And if so, how would it look? And so anyway, the other thing is to incorporate shape evolution into what we're studying. So, you know, studying shape evolution mathematically, it's clear the type of things that you would do, but in terms of 3D print, there's actually a dissolvable filament. So if you printed something in a dissolvable filament, then floated it in the water, then over time, this filament would dissolve. And so we would be able to look at the question of melting using 3D printed objects. So with that, let me just go ahead and acknowledge the support for this comes from the MEGL and the Math Maker Lab, and also all of this was performed at George Mason. And I realized that, so this is our 50th anniversary as a university, and you can see that there's a new future floating print right here in the middle. So thank you very much. Let me go ahead and put up my references. Thanks.
Thank you so much, Evelyn. That was really, really cool.
Thanks.
Does anybody have any questions they want to ask? So I was wondering, when you mentioned like icebergs, do you know if people study, it's probably not like Ricci flow on the surface, but there's probably something related to that, right? That some model that tells you how the iceberg melts.
Yeah, so I haven't looked at that too much, but yeah, definitely. The question of how the iceberg melts is important.
And then what you're doing, then there would be dynamics in what you're doing.
That's right. Yeah. Yeah.
That seems really cool. And so the students working on this now are working on the interface of two fluids?
Well, yeah, so, it's early days, but that's the plan. Yeah.
Uh-huh, uh-huh.
I mean, we just got started a couple of weeks ago, and so, we're still sort of setting things up, but the plan is to do the two fluids case first. It seems like the most accessible. The surface tension case is going to be a little bit more involved in terms of the derivations, but the surface tension case, it seems like the way of doing the the two fluids case, the way of doing this is essentially that instead of only having a center of buoyancy for the bottom layer, you also have a center of buoyancy for the top layer, and then it's just a matching condition situation in order to figure out the potential energy.
Mhm.
And so it's not trivial, right? It really involves some careful thought process, but I think is going to be an easier piece of the project than developing the surface tension equations.
And when you have these two fluids together, is there an analog of surface tension, or does that effect sort of go away?
I suspect that there's an analog of surface tension, but I don't really know.
Because I guess the air is just a fluid too. It's just that the densities are so different, right?
Right. Yeah. Yeah, you can essentially figure that that you don't, I mean, it's negligible, right? Whereas with oil, it's non-negligible.
Evelyn, can I ask a question?
Mhm.
So I think the research is really interesting. Thank you for a great talk as well. So I'm thinking about, again, the two fluid situation. So at the interface, the object is likely to stay there, I guess. But I'm wondering, do you think there could be dynamical scenario, for example, so say one of the fluid is pushing the object a little bit towards the other one, but then the other one repels it back. And then overall, as a net effect, you achieve some sort of local motion along the interface. And as a consequence of the accumulated interactions of small scale effects, you sort of accomplish some type of long range transport along the surface.
So I mean, that is, yeah. So like I don't know. I mean, like, we've just only looked at the static conditions, so I have no idea if that would be possible. I mean, it's an interesting question, but like moving beyond this, but beyond the static case of the potential energy, probably there's just a lot I don't know about how to do that, and so I wouldn't know if that makes, if that is possible.
Okay, thank you. That was very interesting.
So there's trying to think how this works. There's something, so one of this, I don't think it's on this reference list, but one of the cases of looking at the case of sort of surface tension was actually about the dynamics, and it was a little sort of tabletop experiment, which was that basically you can get propulsion by having an object. So basically, if you have a way of locally changing the concentration of the liquid at one end, then you can actually cause propulsion based on the fact that the liquids are different at the two ends. And so what this was is what was called an alcohol boat, which basically had like a little drip of alcohol going out one end of the boat. And as a result, there was this boat moving across the surface. And so I think also with surface, so this is like a surface tension thing, right? Because it's scooting across the surface. And it turns out that some water bugs, actually, the propulsion is exactly because they excrete something on one end, and that propels them across the water surface. And so anyway, I know that that would be an example of something where dynamical studies would make sense. I don't know in the two fluids case if you could have a similar kind of argument that, argument, like whether in practice there is a way of getting propulsion out of the two fluids case.
Thank you. That was really interesting.
Yeah.
So this is actually I don't remember the name of the person who did this, but they actually designed this in such a way that it could even be like something at parties. It was fully edible, this this alcohol boat. And it's not very often, you know, when I read a paper, I sometimes think it's wonderfully clever, but in this case I was like, I so wish I had thought of that.
I think it would be really like what you mentioned about the surface tension, maybe introducing those extra bifurcations so that you were seeing 4 when the theory predicted 2. I would be so interested to see, I will be so interested to see how that turns out. That's
Yeah.
really, really cool.
Yeah, thanks.
Well, does anyone have any other questions? Well, if not, let's go ahead and thank Evelyn again.
Thank you.
And I don't know, Jorge and Emmanuel, does this automatically shut off in a minute, or maybe we have a minute to